You wish to put a 1,000 kilogram satellite into a circular orbit 340 kilometers above the Earth's surface. A. What speed, period, and radial acceleration will it have? B. How much work must be done to the satellite to put it in orbit? C. How much additional work would have to be done to make the satellite escape the Earth? The Earth's radius and mass are 6,370 kilometers and 5.97 times 10 to the power of 24 kilograms respectively. This problem is based on the gravitation. What is happening here? A 1,000 kilogram satellite is supposed to put into the orbit, and the orbit is circular. Having at a distance of, it is at the orbit is at a distance of 340 kilometers above the Earth's surface. Let us consider this be your Earth. This circle will be your Earth. And then the radius of the Earth is 6,370 kilometers. And then the satellite is at a distance of 340 kilometers from the surface of the Earth. So what is the total distance from the center of the Earth to the satellite? We have to add these two. 340 plus 6,370 is equal to 6,710 kilometers. Okay. Now, what is the principle behind this problem? When you are putting the satellite into the orbit, here the centripetal force is required for the satellite to orbit around the Earth. Okay, where from that centripetal force comes? It comes from the gravitational force. Okay, you know, according to the law of gravitation, universal law of gravitation, every object or every, for example, let us consider two objects having the masses M1 and M2, or here we will consider the Earth and satellite. Okay. Earth and satellite, ME is the mass of the Earth and M is the mass of the satellite, and then these two are in the universe. Then these two will attract each other with a force equal to the product of the masses and then inversely proportional to the square of the distance between these two. Okay. Now, according to universal law of gravitation, any two objects, let us consider these two, M1 and M2. Okay, M1 be the mass of this object and then M2 be the mass of this object, and then R is the distance between the centers of these two objects. Then the force of attraction is proportional to product of the masses and inversely proportional to the distance between the square of the distance between these two. Okay, so to remove the proportionality constant, we introduce the constant G, and then G value is 6.67 into 10 to the, I write here, G is equal to 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. Okay. Now, so these two forces are responsible for the satellite to orbit around the Earth. Now we will equate these two. One is the centripetal force, another one is the gravitational force. And then the centripetal force is equal to mv square over r, where m is the mass of the satellite and v is the velocity of the satellite and r is the distance between the satellite and the Earth center. Okay, so Fc is equal to Fg, and then we equate these two quantities, right hand side quantities. From that, we will get V is equal to square root of GME by R, where ME is the mass of the Earth and R is the distance between the satellite and the center of the Earth, and G is the gravitational constant. Now, plugging in the values, we get V is equal to 7,700 meters per second. Okay, so this is the one answer. That is, what is the speed? Next, he is asking the time period. To find out the time period, we use the formula V is equal to 2 pi r by t. we know velocity is equal to distance over time. Here, what is the distance? The satellite is orbiting around the Earth in a circular orbit. So the circumference of the circle is the distance traveled by the satellite. Therefore, the circumference of the circle is 2 pi r, and then the time period is to complete one full circle. Okay, time required to complete one full circle. Therefore, V is equal to 2 pi r by t, and from this we will get t is equal to 2 pi r over V, and then we already calculated the V value, and then R value is known to us. Plugging in these values in this equation, we get t is equal to 5470 seconds. Now the third bit, the radial acceleration. The radial acceleration means the centripetal acceleration. So A radial is equal to V square over R. We know the V, and then we know R value. Plugging in the values, we get A radial is equal to 8.84 meters per second square. Next, V bit. How much work must be done to the satellite to put it in orbit? Now, to find out the work done, we use the work energy theorem. You know, work done is equal to change in energy. So energy means here we have to consider the mechanical energy. So mechanical energy is of two types, kinetic energy and potential energy. You know, kinetic energy is equal to half mv square. And then here, instead of v square, I will substitute this value, gme by r. Okay. So the kinetic energy becomes a half m gme by r. Okay. This becomes the kinetic energy. Now, what is the potential energy? This you may feel strange. This seems to be a new concept to you, or you must have already studied, then no problem. I will explain to you how I got this value. You know, work done is equal to force into displacement for F dot R, or we can write W is equal to work done is equal to mod F mod R cos theta, where theta is the angle between the force and displacement. Now here what is happening? The earth is pulling the satellite towards its center, and then but the satellite is going away from the center of the earth. That means the force and displacement are 180 degrees, making an angle of 180 degrees with each other. Okay. Therefore, theta is equal to 180 degrees. This is the direction of the force. This is the direction of the force. Okay. And then this is the direction of the displacement. Okay. Therefore, theta is equal to 180. Okay. And then we know what is the force here. It is the force of attraction. So that force is nothing but Gmme by r square. And then r is the distance, and then cos 180 degrees. When we plug in this one, we will get cos 180 is equal to negative 1. Am I right? So W is equal to negative Gmme by R is the value we are going to get. So this is nothing but your potential energy. Okay. Now substitute this value here, and then we will get the E final is equal to, substituting these two, kinetic energy and potential energy, we get the final energy is equal to negative Gmme by 2r, where m is the mass of G is the gravitational constant, m is the mass of the satellite, and ma is the mass of the Earth, and r is the distance between the satellite and the center of the Earth. Now plug in the values. You will get the value EF is equal to negative 2.97 times 10 to the power of 10 joules. Okay. Now we have to find out EI. EI, what is EI? The EI means initially the satellite is on the Earth, and later we will move the satellite away. Am I right? So when it is on the surface of the satellite, we have E is equal to this this one. Force, again force into displacement we have to write. Okay. So this is equal to Gmme by r square times r, because our energy is equal to, here we have to consider the potential energy, no kinetic energy. Am I right? Because the satellite is on the Earth and it is still. Okay. Therefore, we consider that the relative motion between the Earth and the satellite is 0, no? So because when the Earth is moving, satellite is moving along with the Earth. Therefore, there is no kinetic energy, only the potential energy. And then the potential energy is equal to negative GMME by RE. And then here RE is the radius of the Earth that we have to consider. And then we have to solve the equation. Okay, here G is 6.67 times 10 to the power of negative 11. And then the mass of the Earth is equal to 5.97 times 10 to the power of 24. And then mass of the satellite is 1000 kilograms. And then radius of the Earth is 6370 kilometers. I converted it into meters. Okay, so initial energy is equal to negative 6.25 into 10 to the power of 10 joules. Therefore, what is the total energy? Here we already calculated the final energy, and we have to subtract this initial energy from the final energy to get the total energy, and that energy, the change in energy, is equal to work done. So 3.28 times 10 to the power of 10 joules of work is done. Work should be done to the satellite to put it in the orbit. That means this much of work should be done on the satellite to keep the satellite in the orbit. Okay, now the third bit. How much additional work would have to be done to make the satellite escape the Earth? Escape the Earth means the Earth has the inherent ability to attract the satellite towards its center. So it should escape from that attraction. That means it should go a height beyond the attraction, where the attractive force becomes zero. Okay, so it goes such a distance, then there won't be any attraction. So that the distance we consider as somewhere far from the Earth. So that is infinitely long distance. Okay. So here you are, so you know, this is the Earth and satellite. Let us consider the satellite is at infinitely long distance from the Earth center, so that it escapes from the attraction of the Earth. Okay. So in that case, then the this becomes zero. This quantity becomes zero, because when we put it, for example, if you see this one, this is the U is equal to negative G M M E by R. Am I right? Suppose if R value becomes more and more, actually potential energy is equal to negative. Okay, negative value. But as R increases and becomes infinitely long, far, then what happens is this fraction value, this becomes 0 as R tends to infinity. Okay, because that's so far we can, I'm not saying that it is infinite, but I'm saying that it is infinitely long. That means far from the at the center. So when this becomes, R value becomes more infinite. Okay, infinite means not infinite. It's so that then this becomes 0. Am I right? As the denominator increases, the value of the fraction decreases, and then it tends to 0. U tends to 0. As R tends to infinity, U tends to 0. Okay. So when U tends to 0, then what is left with? We are left with only this value, this much of energy. Am I right? So to make it, he is asking how much additional work would have to be done to make the satellite escape the Earth. So to escape the Earth, the value should become 0. Am I right? So when the satellite escape from the Earth's attractive force, when it moves far away from the Earth center, then only it will escape from the Earth's attractive force. So to make this, but already it has this and this much of energy. Okay, so it should become 0. Then only it will escape. Okay, so how it will, when it will become 0? So when we do a work is equal to plus 2.97 into 10 to the power of 10 joules. Okay, then it will become 0. Add these two, then this will become 0. Then it will escape from the Earth's attraction. That is, so that much of work should be done on the satellite by the engines. Okay, so when we do 2.97 into 10 to the power of 10 joules of work on the satellite, then it will escape from the Earth's attraction. Okay, So this is the multiple concept question in gravitation. And here the concepts involved are energy, work, and then the universal law of gravitation, and then the centripetal force. Okay, these many concepts, if you have the grip, then you can solve this problem. Okay. Here, this one is this 2.97 10 to the power of 10 joules comes only when it escapes from the Earth's attraction. So when it will escape from the Earth's attraction means when it moves away far from the Earth's center. Okay, so that we consider as infinitely long distance. Infinitely long distance means the potential energy becomes zero. Okay, so we are left with only the kinetic energy or this energy, and then this energy should be balanced. So then only it will escape from the Earth's surface. So to balance this energy, we have to do this much of work. How we do? That means the engines will do the work. The engines will do this much of, when the engines do this much of work on the satellite, it will escape from the Earth's attraction. Okay. That's it. That is the answer for this question. Hope this helps. Thank you. Bye bye.